I'll be talking about transparency and opacity, why objects or substances are either transparent or not transparent, opaque. Okay. The other day I mentioned one clue that Mother Nature gives us, and it goes more or less like this. Okay, we did a little experiment with my wife. Okay, and shown a laser through two lenses that are polarized lenses, and you can see all she does is turn them around, and just by turning around the lens, the beam disappears. Okay, so what I'm saying is that what you got here is one clue that Mother Nature gives us. Okay, that maybe it's the alignment of molecules or atoms, whichever one you want there, that is producing this effect. We're turning something which is transparent into something that is opaque. Okay? That's the idea behind polarization. Now, one fellow out there question that, and he says, polarization has absolutely nothing to do with materials being transparent. Okay? And so he says, transparency is caused by the transmission of light. And again, I showed already in a couple videos, last couple videos, that we're not transmitting anything. Nothing is going through the wall, okay? It doesn't matter if the wall is of cement, bricks or whatever, or if it's air, water, or glass. The light does not go through walls, okay? It doesn't matter what wall you want, okay? And what I'm saying is, you have every material out there, every substance out there is made out of atoms, molecules, okay? And light does not go through molecules. Light does not go through atoms. Okay? Even though, as the religion of quantum holds, and they say an atom is mostly empty space. Well, if that were so, then light should go through everything. Okay? And that's when they come up with all these attempts at explanations, which is what we're going to be debunking here in this session and ones that come after this. Okay, so this fellow continues, says, transparency and opacity of objects depends on how light waves interact with the materials of those objects. Well, we can't talk about light waves. There's no such thing as a wave. Okay, there's a wave. And what you're seeing there is a bunch of vectors that are moving. Okay, what is a vector? It's just magnitude and direction. So for this fellow to talk about waves in the 21st century, he's outdated. He should stay in the 19th century. There is no such thing as a wave. Okay? Maxwell came up, one of the guys, the other one was Fresnel, they came up with a transverse wave. And what is a transverse wave? Just a bunch of vectors, moving vectors. That's math. We don't have a physical object in front of us still at this point. And if you're strong about waves, you got to tell us what that wave is. What is that wave? Is it what I'm showing there, a bunch of vectors? If it's not a bunch of vectors, tell us what it is. Tell us what it's made out of, whatever. Okay. So yeah, this is a problem. People use the word wave. And so let's go one by one here. Here you have waves. I covered this the other day. Airwaves, you can see that the particles of air don't move from A to B to the ear. Okay, what happens is the molecules which are close to the ear are banging against the ear. Okay, so you're shaking all the air that's in the room when you hear me. Okay, and it's those molecules which are close to your ear which are making you hear. It's not the molecules that I'm vibrating here that are reaching your ear. That's my point. Okay. Same with water waves. Water waves, you see there are a couple blue ones in the center, and they're just moving locally. Okay. So even if you're going to use waves, okay, waves don't move like you see there on the bottom left. They're not like those vectors that are moving over. If anything, if light is made of waves or gravity is made of waves, it should be local like you see there with the airwaves and water waves. Why would Mother Nature do something different for light? Okay. Okay, let me get rid of this. And then here's another aspect of it. Maybe what this fellow is looking at or think he's staring at, he's thinking it's waves, but maybe it's a rope. Okay. So maybe this notion that people have that there's waves moving from left to right, maybe nothing is moving. Maybe all we have is a rope that is twirling in place that gives the appearance of a moving wave. Okay? So again, you can't use the word wave until you identify what the object is. Wave is not a physical object. Okay? And then we go to a definition of what transparent is, because this fellow questioned whether polarization has anything to do with transparency or opacity. So we have to look at the definitions here, okay, find out if polarization qualifies. And here you see two sources. Put one the dictionary.com, the other one the Wikipedia. Okay, and you can look up others. I'm sure you'll find exactly the same thing. You can go to the Oxford Dictionary or whatever. Okay, transparency or transparent. What is that? Having the property of transmitting rays of light through the substance. Okay, but it's the only one that mentions what you see there after that says, so that bodies situated beyond or behind can be distinctly seen. The problem with the word seen there has to do with observers, making it subjective. I mean, if we put a blind man and he can't see, he says, well, it's opaque to me. Well, no kidding. Okay, so this seeing thing is something that, whether that has anything to do with transparency. Okay, but we'll get to that in a second. What is opaque? Well, it doesn't mention anything about seeing. It just says impenetrable to the light, not allowing light to pass through, which is exactly the opposite of transparent, meaning that transparent is just when it allows light to go through, not necessarily seen. Okay, and again, it shows that the mathematicians never define words scientifically, and that's why we get into these problems. We get into these problems because we don't know if we're talking about an objective criterion, meaning whether light goes through something. Whether you're blind or not, the light will go through a polarizer, or not, depending on what direction they are. And so it doesn't matter if you're blind or not, because what's happening to the polarizers is independent of opinions. On the other hand, whether you can see something or not, that introduces an observer into the definition. And of course, a mathematician is a person who can't tell the difference between these things. That's why they don't have any rational definitions in mathematical physics. Okay? And Wikipedia, again, doesn't even mention the seen, the observer. It just says the physical property of allowing light to pass through the material. That's what everybody understands for transparent. And what is opacity? The opposite. The measures of impenetrability to electromagnetic or other kinds of radiation, especially visible light. No notion whatsoever whether you can see or not. Okay, so this see thingy is the one that you got to question. Okay, but let's introduce it. What the hell? Let's put it in there. Okay, let's make sure we cover all the bases. Let's accept observers. Okay, if you have two polarizing lenses and you shine a light through, and you're on the other side. Okay, you're on the other side of the two lenses. Well, at one point, the laser hits your eye and you see it. Maybe you go blind. And on the other, it doesn't. Okay, so even if you were going to put the observer into polarization, it fits the definition of transparency and opacity. From the screen's point of view, which is the observer's point of view, which is the opposite end of the laser, right? You either see it, meaning it's transparent, or you don't see it, meaning it's opaque. Okay, so yes, polarization does have something to do with transparency and opacity first, and second, it's one of the clues that Mother Nature gives us as to why some objects are transparent, others are opaque. But to prevent, to get ahead of people out there, it's not the only mechanism. People say, oh, it's not the only mechanism. Let me cover the other mechanism. Allow me a chance to cover the other mechanisms before you open your big fat mouths, okay? And this is the problem. People say, oh, but how about this and how about that? Well, let me get there, okay? And that's why I'm taking it one installment at a time. Today's the second installment. The other day it was polarization. It gives us one clue. Today we're going to look at another clue, okay? If you bear with me. Okay, so let's first make sure one more time that we get rid of the mathematical method, because we're not going to find out how Mother Nature does her stuff with this so-called method that comes from the 17th century. So I'm going to repeat this. You can go take a coffee break and then come back if you've already heard it, but I got to go through this for people who are new to the site. We don't follow the mathematical method here. Okay? We follow the scientific method here. What is the mathematical method? It's the one that's covered in high school and college. Okay? And we have a paradigm shift, and the paradigm shift that says that science is not all this other stuff that they taught you. Science is explanations. What is science not? Well, it's none of these. It's not observation. We don't do observing. We don't gawk in science. We don't look without understanding. Okay, so we don't just say, oh, observe. I observe. That's the first step of the scientific method. No. The fact that you observed doesn't mean that you processed and did something with your observation. We don't do predictions. Okay, science is not about the future, science is about the past. Okay, we do mass extinctions, not the day that humans will die. Okay, among others. Okay? So we don't do predictions. That's astrology. We don't do experiments. In science, we do not do experiments. You heard it here, okay? And no, I'm not drunk. In science, we do not do experiments. Okay? It's in religion where they do experiments. In science, what we do is explain experiments. Okay? There's a difference between doing an experiment, repeatable and otherwise, and explaining it. You have to explain why, what happened, how it happened, okay, in physics. Okay, so doing an experiment is not science. Here, I do an experiment every day, all the time. I let go of the pen, and it falls to the ground. Repeatable, let's do it again. And we let go of the pencil, and it falls to the ground. So I did the experiment. I'm a scientist because I did an experiment. Okay, so doing experiments is not science. It's explaining them that has something to do with science. Okay, and the problem here is that people introduce observation, prediction, and experiments, and they say, oh, we're scientists. I don't think so. Okay, what's the purpose of experiments? Is to create evidence. What's the purpose of evidence? Is it to get your Nobel Prize? The purpose of evidence is to convince the jury. Okay, that's what evidence is for. It's to persuade, convince, convert, and recruit. That's the purpose of evidence. So we don't use evidence. That's religion. Okay? We don't present evidence of the existence of God, for example. Okay, that's not science. Okay, so we don't do any of these things. We don't do measurement. We don't do description. Why? Because it's mathematical description, just an equation. That doesn't tell me how something happened, why it happened, the cause, the mechanism. Okay, so we don't do measurement or math of any kind. Math has nothing to do with science. Math is not the language of science. Math is not the language of physics. The language of physics is illustration. I need to see the mechanism. I want you to make a movie of the mechanism. It's called illustration. That's the language of physics. Okay, for that you need objects. And for that you need to define what an object is for the purposes of physics. Okay, we don't pay attention to credentials. We don't care if you got a PhD, especially if you got a PhD out of Cambridge or Harvard in mathematical physics, for sure. It's worthless. They gypped you. You should ask for your money back. Okay, we don't vote for theories. No democracy in science. And we don't win prizes. Science is not a beauty contest or the Olympics. You know, we don't get medals for running faster or anything like that, for having more knowledge or king of knowledge. No such thing in science. And of course, we don't censor like they do in mathematical physics, especially physical interpretations. We don't censor those from anyone. On the contrary, we want to hear them. We want to hear as many physical interpretations that you can come up with. No math, no equations, no experiments, just the facts. like the policeman, just the facts, ma'am, just the facts. And when we want to, as far as facts are concerned, we're talking about explanation. We want you to tell us a mechanism. You don't have a mechanism, you're not a scientist, you're not a physicist. Okay, so what do these mathematicians use? Well, for the last 400 years at least, for more than that, they've been using particles. But for the last 400 years, they've been using these two, the particles and transverse waves. What's the problem? Well, the first problem is that the particles ain't particles. Okay, quantum does not use particles, corpuscles, little beads or tiny grains of dust. No, what quantum uses are concepts, mathematical concepts that they converted into particles or they represent with particles. That's the first problem. So there is no physical object when they talk about particles. So they chose this word particles, which is very misleading for the common people, because common people say, okay, I know what a particle is. It's only when you press them and say, well, what do you mean by particle? Do you mean like a little corpuscle? And that's when they explain, well, no, you got to take 10 years of math to know what a particle is. That's the way they put it, okay? Transverse wave, I just covered it. No such thing as a transverse wave. All you're staring at is a bunch of moving vectors. So if you're going to go with mathematical physics, they don't have a physical object. They don't have particles, and they don't have transverse wave. We don't have nothing, okay? So this is the problem. So they can't give you a physical interpretation with abstract concepts. Okay, it's important to keep this in mind, okay, because a lot of people use these words, waves and particles, to give a physical interpretation. And unless you know, you understand, you are conscious of the fact that there are no such things as particles and waves, you know, you're going to swallow whatever they feed you. But once you understand that there are no particles and waves, then what you're hearing from these mathematical physicists is bunk, is garbage. Plain and simple, okay, because they don't have a physical interpretation, okay. And so here we go. Here are some of the YouTubers that try to explain opacity and transparency, and they're going to use the particle and the wave. Okay, here you have a whole bunch of them, you know. And here you go in there, just look up why is glass transparent, or why is water transparent, or anything related to these subjects, opacity and transparency, you're going to have all these individuals tell you the party line. They're going to, they're just going to recite what they learned in college, essentially. Okay? And you can look them up in YouTube. You'll find all these folks. The problem is that you don't need to see all these fellows. Okay? You look at one, you've seen them all, because they all say exactly the same thing. And each one starts the same way. They say, if you go to other sites, they'll tell you something that's wrong. Let me tell you the right way. And he tells you the same thing the other guy told you. Okay? So what is the right way? What is the official way of regarding transparency and regarding opacity? Well, here's one fellow. I've talked about him in the past, Mr. Curley. Okay? And what does Curley tell us? Okay, well, he's got his site, and he tells us the following. He starts with his atom. Okay, and you talk about irrationality. Here it goes. Okay, atoms are mostly empty space. Okay, doesn't look like much to work with. Okay, an atom is mostly empty space. Okay, now the next part is what really shows you how irrational quantum mechanics is. Look at this. It says electrons do not have size. Yeah. I've heard it like he said it like that exactly. Okay, these are verbatim. Okay, electrons do not have size. They're point particles. Well, I don't know what a point particle is, but a point, you put a little dot with your pencil, you have something there. And this guy says it's not even that. It's nothing. It does not have any size. No radius, no diameter, no nothing. You're talking, what doesn't have size? Nothing. That's what has no size. It's called nothing. Okay, so he starts out like that. Then he says something even weirder. He says electrons are simultaneously everywhere. Here you have these are his words, okay? I'm not putting them in his mouth. You can look up his video, okay? And it says electrons are simultaneously everywhere. So you have something that has no size, but it's everywhere. Covers the entire universe. Okay, that's, I cannot even imagine what he's talking about at this point. And then he gives, the final cherry on the cake, says electrons can only occupy certain energy levels in an atom, right? So we have something that has no size, which is everywhere, and which occupies only one energy level. Well, that's the end of his presentation right there. I haven't understood anything. Have you? Can you make sense of what he just said? These are his words. And this is a guy who studied at the university. I think he's got a master's at least, probably a PhD. I don't really know. And he makes his money, on the internet. And this is what he tells people out there, what he learned by rote in college. And so he just regurgitates it in language that would be appealing to the general public. Okay, so what is he saying? He's saying electrons do not have size. They're everywhere, but they can occupy, orbitals. They can occupy energy bands or energy levels. Scary stuff. Okay, but let's continue. Let's see if we can find out something about this. Again, you can see there, that's what an atom looks like with the electron rolling around. It looks like nothing, absolutely nothing. So, why does he say this? Well, that's his introduction, because he's going to say, therefore, a photon is going to hit one electron, right? No matter what. Because the electron is everywhere, okay? I thought it was in an energy level, lower energy level, so how can it hit that one? Well, because the electron is everywhere. So no matter where the electron hits, it's going to hit an electron. Where a photon hits, it's going to hit an electron. That's what he's saying. Well, yeah, that's like covering all the bases. I haven't understood anything so far from him. What is he saying? And it says, electrons will absorb the photon, okay? I don't know if I had something else there. Oh, no matter what. Okay. Right, because the electron is everywhere. And so what the electron does is absorb this photon, this energy, because they use the word photon energy interchangeably. Okay, whatever energy is, we never figured that out. Okay. Okay, so this is how he starts his presentation, introducing his atom. I haven't understood anything, but let's see if we can bear with him, see if we can find out what this is all about. Maybe we learned something today. Maybe, at least in the negative way, right? Okay, so here it is. This is his explanation for opacity and transparency. And I want you to pay close attention now, okay? Because this is the party line. They all say the same thing, by the way, okay? Okay, so here goes. Okay, so this is what Curley says. He says, when a photon comes along, the electron gets excited and jumps to a higher energy level. Okay, so it looks like the electron hits, the photon hits the electron, and because of that boost, that bumping, that collision, the electron gets bumped up to a higher energy level. That's what he's saying. This is a starting point, okay? An electron in a gas molecule releases a photon. Okay, so it receives and releases. Okay, we got it. An electron in a liquid or solid molecule, the other molecules are too close, and the electron calms down by releasing that energy to the adjacent molecules. In other words, if the electron absorbs the molecule, the photon, then it's going to use that to shake the other molecules that are elbow to elbow with it. Okay, this increases the thermal energy instead of releasing a photon. Okay, so he's saying now it's absorbed, but instead of releasing the photon and releasing this energy, it uses this energy to do some thermal stuff. It's going to shake the atoms and molecules that are next to it. Okay, it's still absorbed by the electron, but immediately rejected. The energy, here's the important part, okay? The energy gap in glass is too big for visible light. Okay, so you have visible light that goes somewhere from the red to the blue, okay? Infrared is a little beyond our capability to see, and ultraviolet is above, our ability to see. Okay, so it is absorbed by the energy, but immediately rejected. The energy gap in glass is too big for visible light. To excite an electron, the photon has to have an energy of at least 138 nanometers. That's UV light. Okay, so UV light is invisible to us. And so if you want to excite that electron, you can't do it with visible light. You need to get to that edge where visible light becomes UV light, higher energy. And at that point, then, yes, the electron gets bumped to the higher energy level, and that electron or that atom, that substance, becomes opaque. Okay, so this is the issue. Okay, this is how he's going to explain it. And he says, if visible light cannot excite an electron, it won't get absorbed as thermal energy. It still gets absorbed just as vibrations in the electron instead. And since the electrons reject those photons, they make it out the other side. Okay, so if the photon is not absorbed, it just goes through, and that's where all these people get the idea that light goes through substances. And he says, finally, he says, transparency. He shouts it out like saying, that's how you make transparent things. Okay, so let's see if we understood what Curtis said here. Okay, I want people to understand this. Okay, here's a photon. It comes. If it doesn't have the energy, enough energy to strike that electron and push it to a higher energy level, okay, then that photon goes through essentially, and that's in a substance that is transparent. Okay, if instead it hits the electron, well, one of the two, it gets re-emitted, or that electron will translate that into thermal energy and essentially shake the atoms and molecules that are next to it. Okay, and in that case, it's opaque. So opacity turns it into thermal energy at best, or just absorbs it. And in the case of transparency, the photon is not strong enough, not powerful enough, not energetic enough to boost it to a higher level. Okay, we got that? It's important for you to get it. Now, I know some people will want to rush through, but I need to make sure everybody understands it, okay? Because we got a punchline for all these people. Okay, and just in case, want to make sure that this is the party line. It's everywhere. Here you have the same thing from Quora, okay? And a fellow says, why is glass transparent? Okay, dense materials like glass or lead are almost entirely empty space. Great, so everything should be transparent, right? The air and water in the glass are almost entirely empty space. Good, so light should just go through, right? The little photon, the little wave or whatever. The primary reason glass is clear is because it has a large band gap. So we have a difference in energy levels, right? And here's the electron at the lower energy level, and there's a big gap for it to jump to the next energy level. This is the idea, okay? The large band gap is important for transparency because one of the main ways light can be affected by matter is when an electron absorbs a photon. We're going to absorb that photon again, okay? The electron jumps to a higher energy level. You got that? Okay? Higher energy level. And the photon disappears. Okay? So it's absorbed, it's opaque. Okay? The electrons at the bottom of the band gap can only absorb if the photon gives them enough energy. So if it's weak, doesn't have the energy, okay? It doesn't have the oomph to push that electron to the next energy level. That's what they're saying, okay? So they're all saying the same thing. Keep that in mind. They're all saying the same thing. They all went to the same school. Okay, that is only photons whose energy is larger. Okay, it's got to be mightier. Okay, then the size of the band gap can be absorbed. We got that? Okay, I hope everybody is tuned in and understands what I just said. Okay, and I'm going to rub one more in there. Okay, before we move on to explaining all this stuff. Okay, here's the mechanism. I've illustrated it so that you have no doubts. Okay, they're saying here comes the electron. You'll see it in a second here. Hits the the photon and hits the electron. The electron jumps to a higher energy level. This is essentially what they're saying. Okay, and so if it jumps to a higher energy level, it absorbs the photon. Therefore, you don't see that photon doesn't get to your eyes. If, on the other hand, you know the electron does not absorb the photon, then that photon reaches your eye. Okay, so that's the theory. We all got it. I hope everybody got it. Okay. Is there something wrong with this? Let's find out. We'll let Mr. Bean show us why something is wrong with this theory, this explanation. Here's Mr. Bean, okay? And he's in a one-way mirror, okay? So he thinks he's in front of the mirror, but the people on the other side, looking through the same piece of glass, okay? Same thickness, same material, they can see right through the glass. They can see him, but he can't see them. So if I were to shine a laser, okay, from one end or from the other, we would have a different result. It's same material, same glass, okay? You can say what's coated here, whatever, the light is different here. Yeah, I don't care about any of that because we're talking about the material. Here we're talking about the photon from a laser, okay, hitting, being absorbed or not absorbed by the same material from one end or the other end, okay? And so the glass is the same in both cases, whether you're on one side or the other. If I shine a laser from one side, I should be able to see through it. And if I shine it from the other side, I'm going to get a reflection. So we got a problem with this notion that the electron absorbs the photon, because here this is not the case. It absorbs it in one case and not in the other. Okay, but we're not going to stop there. We want to make sure we trash quantum mechanics completely. Okay, so let's make sure we do away with the this theory that quantum mechanics has of absorbing photons. Okay, and here you have a situation, very simple. Okay. And here we have glass, which is opaque. And how did we make this glass? Well, we originally started with a very thin sheet, which is transparent. And the more glasses we put in there, the greener it becomes. Okay, it becomes opaque at some point. If you make glass very, very thick, it's completely opaque. It's only very thin glass that we use like for windows and so on, window panes, that are transparent. Okay, the more glass you put, the darker that glass becomes. Okay, and so let me show you this. Where is it? Okay, you can see it there that if you put one glass on top of the other, it gets darker and darker and darker. At some point, it becomes opaque. Okay, so what happened here? If this is an issue of the photon being absorbed or not absorbed, are we seeing that the more glasses we put, the photon gains energy until it's finally absorbed by an electron, which jumps to the higher energy level? How did that photon gain energy as it went through thicker and thicker glass? You would think it's the opposite. If anything, it loses energy. I mean, you would think, right? But assuming all else being equal, you know, here we have a photon that was not absorbed, but at some point it gets absorbed because you don't see the photon coming out of the other side. Light does not get through that thick glass. It's opaque. And what do they say? The reason for that is that the electron absorbed that photon. And the only way it can do so is if the photon has sufficient energy to boost it to a higher energy level. Okay? So here we have this photon. It's got the same energy that came from the sun, right? From your flashlight or whatever. Okay? And it goes through the first glass, no problem, no big deal. But as it tries to go deeper and deeper and deeper through that whole glass, at some point it gets absorbed and doesn't get to your eye, which is on the other side. But for that, according to quantum, you need more energy. How did the photon gain more energy? By going through thicker glass. Okay? So that's the first problem we got there. And so I ran an experiment, and it goes like this. This is a transparent piece of plastic. Okay? Some material. I don't even know what it is. I don't care. You can see my nose, you can see my mouth, okay? What happens if I put a stack of these? Okay. Can you see my nose and my mouth now? Okay, so one sheet, no problem. Semi-transparent, you could say, almost transparent. Many sheets, not transparent. So what happened to this photon? And it's got trouble getting through. It was absorbed by the electron simply because of the thickness of the layer in front of it. You see the problem? And just in case, did a little experiment. Okay, goes something like this. We have a candle there, and I'm going to put a single sheet of these, and you can see the light of the candle through it. Okay, it's got all these little lines, fine. But when we put the whole stack, you know, you can barely see it, and the more of those sheets that you put, you won't see it at all. You won't see the fire at all. You won't see the light on the candle. Okay, so this is one sheet. Okay, and here are many sheets. Is there a difference? Yeah, of course there is a difference. And what was the reason? Well, the reason has to do simply with putting more in there, more sheets. So we have all these transparent films. The more of these transparent films you put, at some point it becomes opaque. Now, isn't that a magic trick? Take all the transparencies. So the addition of transparent material gives you opaque. Okay, we got that? Okay, here's just in case I did it with a laser. Okay, I pointed the laser at many of these sheets and it doesn't go through. But when I point the laser at one sheet, okay, just confirming here, see, there's one sheet, you can see it goes right through. Okay, so just want to make sure that we're all on top of that, okay, that we all understand that putting many of these transparent films, you can create opacity. So how does the quantum explanation fit into that? Here we have the photon. It's got to gain energy to boost the electron to a higher level. And these people are essentially saying that this electron going through more films gained more energy, enough to boost that last electron to a higher energy level, and that's why the film is transparent, is opaque. Yeah, sure. Okay. And here's another experiment for you to do at home. Okay, this is a very expensive experiment. I don't know if it's within your budget. Okay, and always do it in the presence of a relativist. Never do it alone. Okay, and it goes like this: you get two pieces of tape. The only difference between these two pieces of tape is the thickness of the tape. Okay, I want you to understand that. Okay, the difference is just the thickness. That's it. This one is almost gone. I need to buy a new one. Okay, and this is almost full. Now I want you to see here on this one. Okay, let me show you this. See, you can see the line right through the tape. The tape is transparent. You can see the cardboard line there where the cardboard has been rolled around. See, that's that cardboard inside there, and it's been. You can see it. You can see it right through the tape. This one you cannot see it no matter how you turn it. Okay, so here I'm turning it around, and you can't see the lines no matter what. So even though this is transparent tape and this is transparent tape, bunch of these make it opaque. One of these, or very few of these, make it transparent. Okay, many against the few. Okay, so now we have learned a second way that Mother Nature does opacity versus transparency, and it has to do with how many layers we put in there. One layer, transparent. Many layers, not transparent anymore. And that debunks the nonsense that quantum mechanics says that it's got to do with the absorption of photons by electrons. They would have to explain why that last electron finally absorbed, or one of the atoms in there, one of the electrons in there absorbed that photon. Okay, why? I mean, how is it that by making it thicker, what's that got to do with an electron absorbing a photon and jumping to a higher energy level? By making it thicker, did the photon gain energy? Is that what they're saying? Okay, so here are the conclusions for today. Okay, and it goes something like this. First clue I talked about the other day: Mother Nature does transparency, opacity in polarization. So polarization is one of the clues Mother Nature is giving us on how she does transparency and opacity. Okay, if the films are aligned, you have transparency. If the films are not aligned, one is in this case 90 degrees to another, then you have opacity. And so I asked the following: you can't see through your brick wall, but the question is, if you had the power of God and could align every atom in the brick, everyone is so perfectly aligned in some way, some fashion, would you be able to see through the wall? Because again, light does not go through atoms, through any kind of wall, whether air, water, or glass, or cement. Water is relayed from one atom to another. Okay? And so if we could align every atom in a brick or in the cement or whatever, would you be able to see through your brick wall? That's the question. Okay? Does it have to do with alignment? Well, at least in one circumstance or one situation it does, and that's polarization. By merely rotating or misaligning, right, atoms, molecules, we can produce transparency or opacity. Okay? So that is one clue. Mathematical method, irrational. Okay? You can't follow that to explain, for example, opacity and transparency. Irrational, what is it? To simulate physical interpretation with transverse waves or 0D point particles, which is what quantum mechanics proposes. What does classical mechanics propose? Okay, we're talking about 19th centuriers here, you know, people like James Maxwell and so on. What did they propose? Well, they said, well, discrete corpuscles. But the problem with discrete corpuscles and waves, which is what he really proposed, right? But they were all thinking in terms of particles and waves all the time, okay? You can't simulate the properties of light. You can't do it with discrete particles. You can't do it with waves because there's no such thing as a wave. And you can't do it with zero-dimensional particles, which is what quantum proposes. And so that's the end of those physical interpretations. You can't explain with whatever they propose to date. Okay, and so quantum theory that 0D photons, such as 0D, push 0D electrons to a higher energy levels of or bands is debunked. Okay, it's bunk. Okay, and all we have to do is just put more layers of whatever substance, and we show that it's got nothing to do, in those cases at least, right? Again, we're explaining the second version here, the second installment. In those experiments, those situations, you cannot explain with this absorption of a photon by an electron. Okay? And so, yeah, that's the second clue of Mother Nature, that she does transparency, opacity, by changing the thickness. Okay, so that's the installment for today.